equation. At least I try. Actually, it's impossible if you take it seriously. There's a famous quote by Paul Dirac from close to 100 years ago, who basically made the statement, the fundamental laws necessary for the mathematical treatment for a large part of physics and the whole of chemistry are known, but they're too complex to be solved. And this is true. Even today, if you try to solve the Schrödinger equation for more than 7 electrons, you're lost. But by solving it means by mathematically solving it exactly. So this statement, only within 100 years of diligent work, is still true. The only thing we've changed is we can solve the word exactly. All the Schrödinger equation is too complicated to be solved exactly. But we have wonderful techniques that work well enough to give us good answers for the things we are interested in. So I worked a lot on hydrogen and high pressure systems. And if you plot the temperature here on a log scale, it may be slightly higher than most of you work in, but I'm interested in temperatures ranging from 100 Kelvin to all the way to 10 million. And here's density accordingly. So hydrogen is molecular in this regime here. Then if you add temperature, it will dissociate and it will go into a plasma state that dominates the structure of the sun. And if you lower the temperature, you make it into a metallic liquid. So it's been, they tried to make metallic hydrogen in the laboratory. They've not succeeded. They cracked a lot of diamonds because they do diamond anvil cell experiment and they squeeze as hard as they can and they break lots of diamonds. So the same diamonds you would buy to make your fiancé happy, $3,000 is a cheap one, $5,000 is a real one. They cracked lots of them. So they've not succeeded yet. So we know Jupiter has a large fraction of metallic hydrogen because it has a magnetic field. Otherwise it could not happen. So you know it must exist. So from a calculations point of view, I use mathematical Monte Carlo, the same technique Edgar is working on, except Edgar is following the footsteps of Feynman. This method was used to describe superfluid helium. But ironically, you can also apply it to very hot systems where you treat the electrons as fermions. And then you can describe this plasma state very efficiently. It's not very good to study planets. So that's why I used the more conventional density functional theory, which is just a way of solving F equals ma for the lower part of the phase diagram. And it's very good for planets. It gives us a reasonably good answer for the computational time that we invest.
This is a phase diagram for hydrogen.
This is hydrogen only, yes. So let me say a few, at least one slide about density functional theory. Though you have experts here locally who can explain this much better. So you attempt to solve the Schrödinger equation, and you make one simple ansatz. You just write down a set of orbitals, and so this is a Slater type wave function. It's actually Hartree-Fock on that level, where you just say you have these orbitals in here, like shown here for a methane molecule. And you just try to construct the best orbitals for a given position of nuclei. So nuclei are fixed, and you construct those orbitals. So this would be known Hartree-Fock. And it's a relatively straightforward method. And this is not exact, because generally you look for the best antisymmetric wave function. By writing down those orbitals, you make a gigantic approximation. So by quantum chemist standard, this is already a gross violation of the approximation. By our physicist standards and by the planetary applications, this is quite good. So we're using something better than that. We add some correlation effects that are derived from a density functional. And that gives rise to density functional theory, and it is sort of a cheap way of deriving good results for many particle systems. So typically, we use between 100 and 500 atoms. And that is a good, efficient way of doing it. So we just solve for the electronic orbitals, derive forces, and then solve for F equals ma. We move the nuclei and rederive those forces, and then keep doing the same thing. We can do this on big computers as much as we can get, but it's basically a standard technique at this point. So here's one example for hydrogen. It is molecular on that scale, and the protons are paired. Then if you pressurize the system, Pauli exclusion takes over, and you go into a state where the electronic wave functions are delocalized, similar to a free electron gas almost. And then if you delocalize the electrons, there is no more pairing force between the two nuclei. So then they wander off and they become. So as a result, you have a molecular to metallic transition because the electrons are in a free floating state and can conduct electric currents. So for Jupiter, that is what drives this transition. You have an outer part where the system is molecular, and you have an inner part where it's metallic. So that drives the magnetic field, and you think there is a core. The size of that core is a little bit of a debate, as I will explain. So we know from it's mostly hydrogen and helium. It's like 74%, and then there's 24% helium, and then there's a few other elements mixed in. And I will talk about these few other elements, especially neon plays a special role. So presumably Jupiter recorded what happened during solar system formation. There was a giant cloud, mostly hydrogen helium with a few other things, that collapsed. Most of it ended up in a star. And then Jupiter basically captured some of this gas. And presumably Jupiter and the Sun should have a very similar composition as a result. So we'll come back to that in a little bit. We are a little bit in a scientific debate when it comes to the size of this core. And there's some groups that predict the core is relatively small, and by that standards between 0 and 7 Earth masses. And we claim we have a model that is much bigger. We claim it's 14 to 18 Earth masses. And well, we can either settle this doing theory, or we can actually trust an experiment. And luckily, we're enough. NASA just funded one of those experiments. So just a month ago, or 2 months ago now, they launched a mission. It's called Juno. It takes 5 years to arrive to Jupiter, and then it will be on an orbit that is very elliptical. So it will come very close at one point to the surface of Jupiter, reasonably close. So we'll measure, as a result, what's known as the gravitational moment, to say something about the density distribution of Jupiter's interior, will hopefully give us a constraint how big the core can be. And it does it by the following mechanism. If you have a perfectly stationary planet in a spherically distributed, mass is spherically distributed, then it's a perfect 1/r potential. So then you couldn't detect any mass distribution. But Jupiter is actually rotating very quickly. It only takes 10 hours to rotate once. A big planet, 10 times the size of the Earth. And it rotates in only 10 hours. So that's why you have so many jet streams as a result. But as a result, the planet is slightly oblate. It changes its shape. If you now have a spacecraft that goes around, it can measure the shape of the resulting shape as a result. So they basically track the spacecraft's position very, very accurately. And as a result, can then back out the density distribution of the interior. That's at least one of the mission's goal. They will also measure the magnetic field, and they also detect to see how much water actually is in Jupiter's atmosphere. So what we try to do with simulations is, with observations you cannot probe the deep interior. So we try to supplement that with simulations as a result. And one particular question we are interested in, if this whole gas is collapsing, what processes can lead to an inhomogeneous interior? So we know that the planet is cooling convectively, much faster than the Earth, but still it's a convective process. And what processes on the interior can move mass around besides this overall cooling? And there's, first of all, some people propose there is a first-order transition from molecular to metallic hydrogen. I think based on the simulations, we think that transition is actually gradual, it's not first order. Then we think there is helium rain, and we'll just describe that story in a little while. And then there is possibly core erosion. So core erosion, we mean that you had a core that is thermodynamically not stable if you pressurize it by putting hydrogen on top, and the interior is also hot. So I will describe these two things. So for helium rain, we did not base our calculations, or we did not base our hypothesis on simulations alone. Actually, the story starts with a measurement. So there was a Galileo mission that flew all the way to Jupiter and arrived there in 1995, and it dropped the probe in Jupiter's atmosphere. So the probe sank into Jupiter, and it was crushed at already 40 bars. So basically, it gets very hot. If you drop something in Jupiter, it's like the entry in the atmosphere. Any object basically gets heated very quickly. So it's just a question of how well you build your probe that survives a few more bars. So that was what 40 atmospheres. Then it was no longer functioning. However, it wasn't able to measure the composition. And now we're plotting the composition by dividing the result to the solar value. So we're looking for deviations that Jupiter's atmosphere has compared to the Sun. And we try to say, well, the Sun may have recorded whatever happened to this solar, what happened to this big nebula that collapsed. So for in this case, we find that carbon, for example, is 5 times enriched compared to the Sun. Similarly, nitrogen and sulfur, and also the noble gases. So if you invent a mechanism, so somehow there must be extra material that must have entered Jupiter. That's not that difficult, because...
Can you give me an idea of how far the probe penetrated on your wedge diagram, for example?
You couldn't probably see.
Oh, really? Yes.
Yes. I think the big diagram of Jupiter, yes, you could barely see it. So if you have a picture online of Jupiter that has all those stripes and has the big red dot, it just measured the atmosphere. It did not measure the deep interior. So if you think about the enrichment, there's some process that delivered heavy elements to Jupiter, and that's not inconceivable because Jupiter scatters comets regularly, and some of them get absorbed because they just hit Jupiter. So it's not difficult to enrich Jupiter in other elements. What's difficult to do is to take neon away. So if you look at this diagram, this probe measured 9 times less neon than there's on the Sun. So there must be some process that removed neon from Jupiter's atmosphere. That was unexplained. The probe basically there was a hypothesis that had to do with helium rain, and we followed that route. But there has to be some process that removes the neon. So there's a little bit of a telltale sign. Helium is slightly depleted, but it's very close to the solar belt. So based on that, you could not infer helium rain alone. But neon is a very, very strong signal. Some process must have existed that removed it. If the assumption is true that Jupiter came from this proto-solar nebula, which is a common assumption. So when we started, the idea of helium rain had been proposed previously for Saturn. And Saturn is a smaller planet, and what they detected was an excess in luminosity. So they have a model, when they look at Saturn, for example, how quickly it cools. And there are 2 observations. One is they have a cooling model, and they say the planet should give off this much infrared radiation. And then they compared it to the actual observation, and they detected a significant excess. So there was some process, something that was cooking Jupiter, something produced energy to give extra infrared radiation. They looked for some process, and they only had hydrogen and helium. So the one thing they sort of came up with is that, well, if there is helium rain, then what would happen if you had an intermediate layer, you imagine that helium and hydrogen, normally they mix perfectly well. But if their hypothesis is right, they may demix, and then there would be helium droplets would fall down and would be reabsorbed in the deeper interior. So that as a result, you would move helium from the upper part to the lower part